Oh, welcome back to Sunday Science, everyone. Glad to have you with us. Apologies for the delay in not actually being a Sunday Science show, but being a Monday evening science show. I don't think it matters all that much, though.
I'm to blame for that one, Andy. That was all me.
Well, it happens. It was a worthy cause.
Indeed. It did turn out rather well. It was the crop walk, for hunger in Red Bank there, and we did the communications between all the rest stops. So it was pretty good. Anyway,
very awesome. Glad it was a fun time. So we have a little bit of a kind of a two-part feature here today. We're going to be going over some of the stuff involving LIGO's latest neutron star merger, and also we have a couple of guests with us today, Shawn Hufford and Andy Jones, that have been getting some spectacular footage of reverse crepuscular wave. I hate that word. I can never say it right. It's okay to laugh at me. Crepuscular rays.
Anti-crepuscular rays.
There you go. John's got it.
We got those.
So, as I'm assuming a lot of you know, about a year and a half ago, the LIGO detectors between Washington and Louisiana, managed by Caltech and MIT, made their first groundbreaking discovery of gravitational waves from a black hole merger. This entire project was actually born quite a while ago. I believe in the late 70s was when our new Nobel laureates actually first concocted how they could set up an apparatus of this scale. And it's a truly amazing feat of engineering when you sit down and consider that you're running a laser interferometer over 4-kilometer stretches and having to compensate for the curvature of the Earth and still have sound results to where you're having light frequencies cancel each other out when everything's normal, and then being able to detect gravitational waves as your mirrors side to side are being stretched and pushed and pulled by the force of gravity is pretty astonishing, in my opinion.
It's definitely an interesting play on an experiment from a long time ago. It's quite similar, but the mirror setup is different, which makes it do a different result.
Indeed, and doing digging on this a long time ago, I remember hearing from one of the physicists that was involved in the original construction that in some of their first attempts at actually building an interferometer of this scale, they were trying to manually adjust their mirrors. And I can't imagine being one of the technicians sitting down and attempting that and actually trying to manually adjust a mirror at that distance to...
I'm just getting a flashback of my mom saying, a little to the left.
Yeah, right? Something like 12 different adjustment knobs and trying to orient everything properly, trying to center everything properly. That must have been an absolute nightmare. But, of course, now in both the Hanford Observatory and the Livingston Observatory, everything's fully automated on that portion. It's still a daily task where the mirrors have to be calibrated every single day when they are running observations. So, why don't we go ahead and cue up one of my favorites when it comes to just chit-chatting about this stuff in general. It's from PBS Spacetime, and it's LIGO's first detection of gravitational waves. I think they do. If you don't already subscribe to Spacetime, I would highly suggest it. And if you don't, then you're about to probably find out why you should.
All right, here it comes.
Some incredibly exciting news today. Gravitational waves have been directly detected for the very first time. The Advanced LIGO Observatory has seen the space-time ripples caused by black holes at the moment of merger. The existence of these waves is the last major prediction of Einstein's theory of general relativity to be directly verified. A century after the theory was first developed. it opens a whole new window through which we can now observe our amazing universe. This is one of the most important observations of the century. On September 18, the Laser Interferometer Gravitational Wave Observatory switched back on after 3 years of upgrades. The new advanced LIGO is around 10 times more sensitive, and even conservative estimates predicted that it should certainly detect the passage of gravitational waves, of ripples in the fabric of space-time, caused by extreme gravitational events in the distant universe. Almost as soon as it was switched on, a signal was seen. The LIGO team kept very quiet and continued observing. LIGO has been cautious, and when here at Spacetime we realized this was probably the real deal, we were too. However, soon after the detection, we put together a video explaining what gravitational waves are, how they're formed, and exactly how advanced LIGO detects them. It's right here. This is a great time for you to watch it if you haven't already. That was 4 months ago. Since then, ripples from mergers of black hole pairs in distant galaxies have changed the shape of space-time here on Earth, indeed across the Milky Way, and LIGO has seen them. Today, I want to talk about what exactly was seen, what it tells us, and what we can expect for the future. Any orbiting pair of massive objects generates gravitational waves, but only extremely massive objects that are orbiting extremely close together produce gravitational waves strong enough for us to detect, at the moment. Now, LIGO is sensitive to pairs of stellar mass black holes and/or neutron stars. In both cases, these are the collapsed core of a dead star, stellar remnants. Now, these stellar remnants are sometimes found in pairs, typically when the original stars were also a binary pair in orbit around each other. These super-dense objects produce serious gravitational radiation, but gravitational waves carry energy, which is sapped from the orbital energy of the system. As a result, the stellar remnants will gradually spiral in towards each other. Now, we've seen this slow orbital decay in binary neutron stars. The amount of energy being lost in these systems is exactly what we predicted should be if caused by gravitational radiation. And so this was a very convincing but indirect verification of gravitational waves. However, the waves produced when these stellar cores are still distant from each other are far too weak and have too low a frequency for LIGO to directly detect them. But as the cores get closer, the gravitational radiation becomes extremely intense. The in-spiral speeds up exponentially, and the last phase of the merger takes only a few minutes. In those few minutes, the merging black holes or neutron stars produce such strong ripples in the fabric of space-time that LIGO can see them out to vast distances. In the case of merging black holes, to 5 billion light years. Now this is really an insane distance, but that's just as well. These events are incredibly rare. It's expected that an observable merger of two black holes will happen only once every 10,000 years in any given galaxy. So we need to watch a lot of galaxies. Advanced LIGO can feel the ripples produced by merging black holes through a volume of space equal to about 0.1% of the observable universe. That means we're watching millions of galaxies. In the case of merging neutron stars, it's a much smaller distance, and so none have been seen yet, although it will happen eventually. We'll also spot supernova explosions that produce neutron stars. Stand by for that. Now, these mergers have very distinct signals. They cause actual physical distances to change. Space-time is stretched and squeezed as the wave passes by. These oscillations have a frequency, number of stretches and squeezes per second, that matches the rate at which the black holes are orbiting each other just before merger. And we're talking up to 1,000 orbits per second. Okay, so we saw some black holes merge. That's pretty cool. But what can we do with that? Well, everything else aside, it's a great vindication for Einstein's general relativity. See, gravitational waves are inevitable if the theory is correct, and they were the last major prediction not directly verified. If they weren't seen, it'd be a huge problem. Okay, so Einstein wins again, except that now we have the capacity to do detailed tests of general relativity in a regime previously unavailable, in the regime of extreme gravity. If the merger signals deviate significantly from the expected signal, then it may be a clue that the theory is incomplete or even point to a new, deeper theory. Now, as far as I know, there's no indication of that from the detected signals. However, physicists will be all over this data looking for holes in the theory for some time. These observations are going to tell us a ton about how black holes grow and about the physics of black holes themselves. The signals are expected to carry information about the strange warping of space in the region of the event horizon. Before long, we will observe one of these mergers simultaneously using multiple telescopes that span the electromagnetic spectrum, from radio to visible to X-ray. And that observation will break open so many mysteries and no doubt reveal further new mysteries. Now, LIGO is sensitive to gravitational waves at frequencies produced by merging black holes and neutron stars, as well as the formation of neutron stars in supernova explosions, and potentially even the actual spin of neutron stars. However, now that we know that these things are detectable, it opens up an entirely new spectrum for observing the universe. The upcoming Evolved Laser Interferometer Space Antenna, ELISA, will see an entirely different part of this spectrum, much lower frequencies, opening the possibility to observe completely new phenomena. It'll see the slow ringing of binary white dwarf stars in our own galaxy, as well as the final dance of pairs of truly gigantic supermassive black holes just before they merge in the cores of galaxies. It's hard to understate this. This is a really, really big deal, and it marks the beginning of the era of gravitational wave astronomy. It's a new window on the universe that will reveal phenomena and physics that we never expected. We'll keep you up to date on future episodes of Spacetime. In a recent episode, we heated up the debate on the question of settlement of Venus versus Mars by looking at some nice ways to die on both planets. You guys had some great questions. The Real Billeth asks, wouldn't Mars's low gravity mess up bones and muscles? Now, this is a really good point that I didn't mention. In terms of a long-term colony, Venusian cloud cities are going to be much healthier. Astronauts on the International Space Station lose bone mass at 1 to 1.5% per month and lose muscle mass also. It wouldn't be so bad on Mars, but a long-term stay may be very unhealthy. Venus's surface, or even cloud city gravity, is 90% that of Earth's, and so the bone and muscle degradation would be minimal. Laura Lorca wants to know exactly how to build a cloud city. Short answer, balloons. In fact, a giant balloon filled with atmospheric pressure air would float nicely at around 50 kilometers. So, think a huge dome filled with a breathable atmospheric pressure air on an even larger balloon base. It could be tethered to the surface with heat and pressure resistant cables, carbon nanotube cables perhaps. NASA is already thinking about small floating missions. Check out its HAVOC program in the link below. Fabio Brady would like to know whether Martian sandstorms are really life-threatening. So those sandstorms may be huge, but they're really more dust storms than sandstorms. The atmospheric pressure is so thin that it doesn't generate enough force to move big stuff. Not large grains of sand, and certainly not people. This was a bit of creative liberty taken by the otherwise really awesome movie, The Martian. Astrophysicist Andy Howe does a great job detailing the science of The Martian in this video. His channel is really excellent.
Nice.
All right, so obviously this was a little over a year ago now, about a year and a half or so, when some of the first groundbreaking information was finally coming out from LIGO after their upgrades. And I thought this was going to be a fun one to bring in as our latest breakthroughs that is finally released in public statement earlier today actually did wind up being a confirmed merger of two neutron stars, as opposed to previously LIGO had only detected gravitational waves made from black holes. So I thought this would be a fun way to jump in where it was still in the still in the theorized point where, okay, we have actually proven we can detect gravitational waves, and we believe they can happen this way. And as of today, it has been proven, well, even though the events actually took place in August. You know, science takes a little while to double check your data when it comes to scenarios like this. And it is truly confirmed, and some of the really cool stuff, I think, when it comes to the merging of neutrino stars, the way that the periodic table of elements is not evolving as far as elements that we know, but as far as how and when certain elements actually do get created. And that's where I was hoping we could jump into LIGO's latest hit film. Andy Jones, I know what you had for a little later. If you're seeing any of that, I would say catch it on film. It probably won't be sunset anymore.
Nope, it already got dark, and I was out here actually before sunset looking for it, and it was really faint. Yesterday it was a whole lot better, though, so we didn't miss anything.
Well, we still got some great pictures over in Science Strike Force that we can share for that, and Shawn happens to be really good at catching these as well. I've seen it once, but before we get into too many spoilers, why don't we take a look at what LIGO was able to finally confirm with the ESA and multiple astronomers across the planet. This is absolutely awesome. If you want to roll the next one there, Sai.
Absolutely. Here we go.
LIGO's hits just keep on coming. After its first detection of merging black holes, swiftly followed by finding 3 more, and then a Nobel Prize, the pair of gravitational wave detectors has made yet another huge discovery. On August 17, 2017, the observatory detected gravitational waves from 2 neutron stars spiraling together and merging. Just 2 seconds later, a so-called gamma-ray burst was detected by NASA's orbiting Fermi Gamma-Ray Space Telescope and its Swift Space Telescope. 12 hours after the wave was detected, a team from Las Campanas Observatory in Chile reported a new glowing optical source in galaxy NGC 4993 that was consistent with these findings. And with the advanced tip from LIGO, both radio and X-ray emissions were found a few days later, coming from the same neighborhood. Not only is this the first time LIGO has detected gravitational waves from a neutron star collision, it's also the first time that electromagnetic observations from conventional telescopes accompany the gravitational waves. At wavelengths ranging from ultra-short gamma rays to very long radio waves, the event was seen by observatories around the world. Because we now have visual information to go along with the gravitational waves, new discoveries are being made about the nature of neutron stars. The light coming from the collision showed spectral traces of lanthanides, a group of heavier elements towards the bottom of the periodic table. This strongly suggests that merging neutron stars have been responsible for the creation of heavy elements such as gold and platinum, a long-held theory. Not only that, but the shape of the gamma-ray burst was unusually weak. Gamma-ray bursts are usually so strong that researchers assume that the gamma rays emerge from 2 back-to-back jets that shoot out of an explosion like narrow spotlights. The weaker gamma-ray burst suggests it was produced when broader jets slammed into a cocoon of matter surrounding the merged neutron stars. While this finding is home to a lot of firsts, it won't be the last. Researchers are positive that with the large amount of gamma-ray events out there and the increase in both gravitational and electromagnetic detector sensitivity, we'll be seeing a lot more of these combination events in the future.
You gotta love when you forget to sit down and unmute yourself.
Indeed.
talking for 5 seconds, going, "Wait a minute, what's that red thing?"
You probably said something really impressive too, didn't you?
Oh no, it was absolute gibberish.
It was really good.
I bet it was profound.
All right, so yeah, big news today.
It was a big news day, and this is pretty amazing stuff, I think. And there's just a plethora of videos coming out today covering all of this, and as much as I would like to cover a dozen of them, hopefully we can get some minds thinking about looking into this on their own, and they can go out and discover some more of these videos themselves and start learning this stuff more at their own rate, at their own want, as they so choose. So just wanted to share the two today, and obviously there's a lot more about interferometer technology that I would love to get into and love to talk about. The one that I would suggest that kind of goes with our closing of the day with simple science. If you go to LIGO's, I think the one I was looking at was LIGO Caltech's website. They actually have a link for a try-at-home experiment where you can actually get plans to build a miniaturized version of the laser interferometer that they use. Well, it's not actually one that they use. Technically, it's a magnetic Michelson interferometer, but for anyone interested in sitting down, I've already downloaded the PDF, and I've built a couple of interferometers in the past, but not this particular style, so I'm probably going to wind up building this one just for fun and kind of see where it goes. I'm not sure. Let's see, maybe if I can present here for a second.
Oh, hold.
I love how you're always just like, screw it, I'm going to build it. I'm going to build it myself.
I love building stuff. Absolutely love it. All right, so here's the PDF laser interferometer, the magnetic Michelson interferometer that's on Caltech's LIGO website. And I haven't actually gone through the whole thing yet, but I think it's definitely going to be fun. I'm really looking forward to sitting down and building this. It kind of goes hand in hand with another experiment that I've been looking at doing that's kind of a manipulated version of the Cavendish mechanism. So we'll see if maybe I can play with this and get some of the results I was looking for. But yeah, if you go to LIGO's Caltech page, I'm not sure if it's on their MIT page. I don't think it's on either of the observatory pages, but yeah, if you hit up the educational resources and try at home. I was playing Black Hole Hunter earlier. It'd probably be fun for some kids. It was just kind of loud and hurt my ears, but you know, I'm not as young as I used to be, but they have a lot of fun stuff here. I'm looking forward to heading over to the MIT page and seeing if they have the same try-at-home projects or if they're running different ones. So thought I'd share that real quick before we jump over. And not sure, Andy, if you have links to your images or if Shawn wanted to start, but I'm going to go ahead and let you guys, because I've seen this phenomenon one time, and I kind of didn't believe what I was seeing to be real. I thought maybe something else was going on, like a concert, and it's been solidified more and more between you and Shawn now. So I'm going to go ahead and let you guys take the floor on this for a little bit and let us know what you've been seeing in the sky lately.
Well, mine's not lately. Andy's is a lot more recent than mine is, but I haven't seen his yet, but I'm going to say mine's more spectacular.
Is that what we're looking at right now? Is this one yours?
Yes, this was taken with a drone at 50 meters above the ground, the day of the eclipse, so August 21st. And Yeah, the sun has been set for about 30 minutes at this point. We're talking below the horizon, not just past the mountains. The sun actually sets past the mountains about 4 minutes before actual sunset from the horizon. But yeah, these shadows are coming from 3 states away. And we were on...
Well, the shadows are actually coming from behind you, correct?
No, these are actually the corpuscular rays. I'm going to show you the anti-corpuscular rays here in a second.
So where's the sun in that picture? Is it behind you?
No, the sun is actually in front of us at this point.
Okay.
Let me actually pull the picture where I can show you the convergence lines. There's where the sun is.
Okay.
And this is, yeah, this is an awesome little accidental finding, because we just looked up when we were coming back from the waterfall, and there it was. This is the anti-corpuscular rays.
Okay.
But I've actually made them into a little bit higher contrast to make them easier to see. And that would be these.
You know, I think it was during a movie night that I brought up anti-corpuscular rays and was laughed at. And it was just earlier in the day that I was sitting there looking at it going, what is this?
At this point, the sun is directly behind the drone.
Okay.
And that's where they're converging at. Which really made a lot of people cry. And the best part about this is we actually have the Terminator shadow in the sky, right there.
Ah. I didn't even look for that.
Well, I didn't even know we got it either until I actually made this into high contrast.
Okay.
But yeah, that was really, really impressive to catch that.
Yeah, I'm gonna have to play with mine more.
Real quick, sorry to interrupt, guys. Could I get a Side Strike? Could you give me a chat link real quick? I seem to have lost it.
Oh, sure. Hold on 1 second.
Are you not subscribed to Side Strike?
Well, I am, but
you got to put in live.
I have a lot of reverberation because I'm basically in a concrete corner, so.
All right, here, I'll put it in the...
I'll actually load the video for this because this was really, really neat to catch too. Let me hide that.
There you go. It's in the...
Thank you. Much appreciated.
Not a problem.
Oh, yeah.
Oh, yeah, and Andy, not Andy. Andy, you have a little wind noise on the microphone. I'm noticing.
That might be me.
Yeah, that's when see, I was talking to Andy, not Andy.
That one could get confusing.
Indeed.
If you look here, this is when we're actually rotating the drone to face away from the sun. We actually have the Terminator shadow going into the sky from right to left, going higher up on the left. We have a nice cone shadow. This is looking due south at this point.
Do you have the straight up picture that shows them to be parallel overhead?
Oh, of course.
That would be a handy one. That's
I believe it's this one. And this is my daughter standing in the picnic table, or on the picnic table in the center of the yard. And yeah, she actually turns a full circle, looking at both the rays. Oh, maybe it was the other one. Yeah, it's the other one. I grabbed 2 from her phone. There we go. That's south. That's east. That's north. And back to north. And then she goes west and then back to south. And of course, she has to say in the middle of that, at the end of that, I win for having the best footage.
That was an amazing day, was it not, Shawn? I mean, you would think it would be
That was
anticlimactic. After the eclipse, everything else, we figured, oh, well, that's it. It's all going to be dull from here on in. And then that. That's and then once again, compliments for that expedition you organized.
Anytime.
So basically, this is like train tracks, you know, going past you, but the sun on one side, and then the lines are actually parallel,
Yes.
but they look like they're coming to a point on both sides. Like if you're standing on a train tracks, you're going to see, you know, the same on both sides. So even though the sun's behind you, you know, those parallel lines are still looking like they're converging ahead of you. It's not because the sun is 3,000 miles above the planet, obviously.
No, it's probably not that.
Try to rule that one out.
As I recall, Shawn, were there not many flat Earth tears over this new evidence?
Oh, there was many flat Earth tears.
Indeed.
Aren't there pretty much always flat Earth tears when you go out and do science?
Well, yeah.
Well, they're so good at denying, though. I mean, you know, that's fake, or... And you know what I didn't do? In my video, I did pan around about 90 degrees, if you guys saw it. But I should have turned all the way around to show the sunset, the real sunset, and then turned back around to see the, you know, the lines on the other side. But I mean, that blows that whole thing out of the water.
Well, yeah.
Pretty
much.
Not that we needed anything to, but yeah.
Well, no, what made it so humorous, though, is I had that footage and I was deciding on what to do with it. And then a flat earther declared what we should see on the if the Earth was a sphere. And it's exactly what my footage was.
That's awesome.
So yeah, that worked out really, really well.
Especially when they say it first, you know.
Right. Well, do we have... It sounds like you might be on your cell phone, Andy. Do you want me to hop over into sharing some of your pictures that you were able to get of this awesome phenomena? At least I can see the ones that you put on, you know, on Strikeforce.
Did he mute?
You were muted, Andy. Not Andy, but Andy.
Sorry, I had my microphone off now too.
No worries.
Yeah, if you could do that, that would be awesome. It was only those two pictures, or one picture and one video.
Well, let's take a look.
Yeah, I was surprised when you showed me yours how similar they were. I was like, yeah, that's the exact same thing.
So have you figured out what was causing yours yet?
Well, I assume, you know, there were clouds everywhere. And so to my back, you know, you got these big clouds with the sun. Even though the sun set, you know, at elevation, it didn't set yet. So you're seeing those, you know, those straight lines, the shadow of the cloud.
I'm sorry, I just interrupted you. I was looking at the picture that you put up in here, and I'll actually start presenting.
Okay.
So you can see this. Okay, so here's your picture that you had put up for all of us to take a gander at, and even without having to do any contrast adjustment, you can still make out the Terminator shadow line that's starting to
it
break
crosses the whole horizon
right here.
Oh yeah, yeah. I didn't notice that.
Yeah, you see the Terminator shadow right before where they converge, and then you see it off to the left as well.
Yep.
Right, off to the left is where it's the most clear, I think.
Yeah, I didn't notice this at first when I was looking at it on my phone at work, and
Yeah, catching anti-crepuscular rays converging to a point is really, really rare to get. That's because you have to have the lighting at just the right angle without actually intersecting a surface of the Earth somewhere else before or after where the shadows are being caused from. So it's really a matter of perfection on timing.
Well, it sounds like you got pretty perfect timing there, Andy.
It's luck. Well, like I said, I went out today, to see if, because I was thinking, hey, maybe this is something that happens every night. I'm just too stupid to see it, but, I guess it's not every night, but I don't know why. I mean, there were the same clouds up today, as yesterday, but.
Well,
I've seen it once in my life, and I thought I was absolutely crazy. And like I say, when I brought it up on movie night, I actually got laughed at a little bit. And this was before the eclipse, so.
Here's the thing about the timing on it, though. You have to make sure that you have clear skies from your location to wherever the shadow is being generated from, and then beyond that, it has to be clear as well. So you just happen to catch a storm system that was building up at just the right time where there wasn't storms to the east of it or to the west of it, so it was able to make these shadows.
So there's storms behind me, but not in front of me, is what you're saying.
Well, no. From your location all the way towards the sun, you have a clear section, then you have a cloud, and then you have a clear section beyond that.
Okay.
Yeah, it doesn't matter what's in front of you at this point because you're looking away from the sun. It's just towards the sun, it's very specific conditions you have to reach. And you got lucky. With the ones that we had down in Tennessee, those are actually kind of common because, at least during this time of the year. One more day before or after the eclipse, we would have never seen them because those were actually generated by mountain peaks.
Oh.
In Missouri.
Jeez.
Yeah.
You see that every day. I mean, any day that it was clear, then you would see those, right?
Well, no, Missouri's like 1,000 or so miles away.
Right.
And it was past sunset there too, but those mountain peaks were high enough to where they were still peeking out and getting direct sunlight.
Right.
Which is why we had a flat Terminator shadow as well as those peaks.
Oh, okay.
But one more day and the sun would have been at a different angle when it was setting, so the rays would have actually shot north of our location because it was traveling towards the south. And one more day before, and those shadows would have been too far south to see from our location. So it was just a matter of perfection on timing. And it was totally accidental.
The sun and the mountain and you all have to line up, in other words.
Correct.
Right. Okay. That is really cool.
So yeah, I'm actually hoping to get back down there next year to see them again on the same date.
Yeah, I didn't even think about that. Like actual, mountains and things like that causing shadows. But
yeah, those are much more rare because you have to have perfect conditions between you and the mountains, and then past those mountains to be able to get direct sunlight to the mountains.
Right. I got you. Now, does the atmosphere have to be a certain, to have the line in the atmosphere, like at the picture we're looking at?
Well,
does there have to be a certain mist or something, like to see the lines?
Not really so much because nitrogen reflects everything in blue anyway.
Okay.
And as long as you got Rayleigh scattering going on, you're going to see those crepuscular rays.
Okay.
So as long as there's direct sunlight and a high contrast shadow, you're fine.
Okay. That's really cool.
And you know what? The one thing I really wish we would have done with that drone flight, Si?
What was that?
Let it sit up there for another 10 to 15 minutes and watch the shadows continue to move upwards and finally fade out.
That would have been pretty cool.
Yeah, that was just after a charge. We actually had enough battery left in the thing to do that.
Yeah, but we were excited and we wanted to see the footage.
Oh yeah, absolutely. And you're very lucky. Very lucky day that was.
This has me tempted with the drone capabilities and 360 camera technology now, that could be a really fun one to try and spend some evenings capturing crepuscular and anti-crepuscular rays at the same time via drone and 360 camera.
Well, two things.
Yeah.
With a 360 camera, as everybody that was down there in Tennessee found out, using a add-on camera on a drone really doesn't give all that great of footage. It's too shaky because it's not running on a gimbal.
Yeah, that was true.
Chris Hartner was doing that.
Go ahead.
Chris Hartner was doing that. I know he uploaded some stuff from the Eclipse where he had a drone with a 360 camera on it.
We did as well. It's just one, it showed some faces that we didn't want to have put out there, so we had to take the footage down.
Right.
And we couldn't figure out how to edit those faces out without losing the 360 tag.
Right.
So it wouldn't show it was a 360 video anymore. But Sai actually has the 360 footage, and it's really, really neat. It's
in fact.
Really shaky.
It was a last-minute decision. Hey, let's send up the 360 cam. And
now, to be fair, everything about that drone was a last-minute decision.
That is true, and it didn't. Most of it turned out pretty well. The 360 cam was not a. I won't classify that as a failure, and I am going to have to.
Oh no, it's not a failure. It's just it could have been better if we would have had more time.
Yeah, if we could have made a little better mount. But agreed. Anyway, but that was it. It was very fortunate that we happened to be there on that day, and most fortunate that Shawn seems to notice little details like that.
I notice everything. It's annoying.
Oh, it happens. So, Andy, do you want me to share the video that you got of this as well?
Sure, if you want. It's only a quick, 10-second clip or something?
Yeah, either way.
Sure.
And now you're looking north.
Exactly, yeah.
I'm just looking for the cone shadow, which you don't seem to get a whole lot of. It's not any fault of yours.
That angle.
I just think it's the time of sunset that you're dealing with.
Okay.
Plus,
Yeah,
it was.
I should have went all the way around.
That you said that was the blockage of the light was from intermittent dense clouds, right? Probably is that not what you said?
I think that's what he said. Me? Yeah.
Yes, you. Okay,
There were clouds. There were clouds behind me. Yes. So I assume that that's what it was.
I'm just
thinking. The telltale sign for that, Sai, as far as why I can tell it's clouds, is because you'll see bands of light between them. Mm-hmm. You'll see darkness, light, darkness, and then it kind of fades into lightness, and then it goes back to solid darkness all the way across the sky.
Yep.
In that frame you got right there. That's usually a telltale sign that it is clouds causing it.
Yep, that's where I was going with that. Whereas the with a nice solid mountain or a couple of them blocking the rays, it's a hard stop. So that's interesting that you can not only tell that you do in fact have rays, but you can judge the cause based on the image. Anyway. Nice.
It's really cool. It's really cool to just see something and take a picture of it and have smart people online tell me what it was. It's just cool knowing you guys and having intelligent people to, I would have never even thought to ask the question until I saw it yesterday, so.
It's good you had the presence of mind to say, this is something that should be recorded.
Yeah, I'm glad I did.
Indeed.
It's definitely worth getting the pictures and taking the recordings. I tried taking pictures the one time I've seen them, and I had the white balance all off on my camera, plus the camera I was using doesn't have an IR cut filter, so it really makes clouds look horrible, and you can't see much of anything in them. Glad I got another one, because that was getting annoying. Also doesn't help that when I pulled the IR cut filter, I accidentally discharged one of the flash capacitors, burned up the LCD screen's control PCB. That kind of stunk.
A little bit.
I would say.
But I always run it through a laptop just for astrophotography, so I'm not concerned with what I can see on the LCD screen. It's running in bulb mode through Backyard Red, and I see exactly what it's imaging on the laptop screen. That's a lot easier to look at than a little 3-inch LCD.
Right. We're not all geniuses like you, though, right?
I don't think I'm all the way to genius level. I think I'm.
Oh no, you are.
I think I'm a weirdo.
Oh, Andy, we all bow to you.
Well,
no.
I don't know what to say to that one other than thank you, I guess.
Yeah.
All right.
No, go ahead. Is that a night?
You know, as much as I wouldn't mind getting back into the technology, it is, you know, this is normally a middle of the day kind of show as opposed to a evening show, and I am getting kind of hungry. I'm not sure about the rest of you. Does anybody else want to add something in there or have any questions?
I think we're good.
I don't think so.
What about chat? How are they doing?
Didn't see any questions so far.
Terminator Shadow does not need to be Austrian shaped. It's more of an Austrian-American immigrant shape. Yeah, other than that, aside from everybody listening to me geek out about interferometers, I don't think anybody really wants to hear that. We're probably about good, I think.
All right.
You have... All right. Oh, we should put, by the way, the link for that PDF, we should probably add that in the description when we're done as well, in case anyone wants to go look for it and build their own.
I can...
Give it to me after. I'll put it in the description.
Okay, that works. I already have it copied.
Alrighty then.
Oh, is it time for Simple Science?
Did you did you have one more thing queued up, I think, to show? Not sure, a Hubble one, I think.
Oh, I did, actually. I did. Why don't we go ahead and watch that and then Simple Science?
Alright, so shall it be.
So, we're kind of going back to LIGO now, and, well, not actually LIGO, but part of the discovery process for finally being able to see in the visible electromagnetic spectrum of this amazing event.
Indeed. So here we go.
Astronomers using the NASA ESA Hubble Space Telescope have observed a visible counterpart to gravitational waves for the first time, a kilonova from merging neutron stars. On August the 17th, 2017, the LIGO-Virgo collaboration detected gravitational waves rippling through the fabric of space-time. Just 2 seconds later, 2 space telescopes from ESA and NASA also detected a short gamma-ray burst coming from the same area of the sky. This coincidence had never been seen before, and raised hopes that astronomers had witnessed a cataclysmic event. 2 neutron stars combining in an explosive merger. If so, a visible light counterpart known as a kilonova was expected to follow. The hunt was on. Hubble joined a host of telescopes from the European Southern Observatory and other observatories around the world to search for a new light source. They were looking for a needle in a haystack, a faint new glimmer amid millions of stars. But amazingly, they found it just a few hours later, in the galaxy NGC 4993, 130 million light-years from Earth. Over the next few weeks, astronomers used a host of telescopes to record the kilonova. Neutron star mergers are the furnaces where most of the chemical elements heavier than iron are forged. The kilonova, an event 1,000 times brighter than a typical nova, spreads the newly formed elements into the surrounding space. These include the gold in jewelry, the platinum in catalytic converters in cars, and uranium in nuclear reactors. Such an explosion had never been confirmed before, but now one could be studied in great detail. The observations revealed an extraordinary and rapidly changing event, closely mirroring theory. Heavy radioactive elements were shot into space at 1/5 of the speed of light. In just a matter of days, the kilonova's color changed rapidly from blue to red, faster than any other observed stellar explosion. This event marks the start of a new era of multi-messenger astronomy. For the first time in history, we can now combine light signals with gravitational waves to provide a totally new way to probe the universe.
Alrighty, wanted to share that one up. I'm pretty sure everyone watching knows exactly why I would want to share that one. Like I say, there have been so many videos coming out today on YouTube in regards to this subject that trying to sift through them is going to take a normal person a couple of weeks, and there's going to be a tremendous amount of information in there. So, that being said, I believe you have a science project for us, Si?
Indeed, I have one, and once again, apologies to all the big brains present here and just watching. Keep in mind, this is simple science meant to introduce the younger folk to the concepts and hopefully spark conversations. This is the second in the magnetism series. We had the relatively weak homopolar motor last week, and this is the next step. Here we go. Hi there, and welcome back to Simple Science. Today's project is a small electric motor that will be slightly more powerful than the homopolar motor that we constructed in our last episode. Alright, as usual, we will start with what supplies you're going to need. First, you will need a cigar box, 2 paper clips, 4 neodymium magnets. If you did our last project, you should still have these around. A spool of 22 or 24 gauge magnet wire. This is the type of wire that is coated with enamel instead of a plastic insulator. You will also need 2 push pins. Any small cylinder that is about a ½ inch in diameter. You could use a magic marker, for example. 2 D-cell batteries and a battery holder. 2 jumper wires with alligator clips at each end. And just like in many of our projects, you'll be needing your scissors and small needle nose pliers again. Well, that's about it for supplies. Let's get building. Using your small pliers, bend the 2 paper clips into an L shape as shown. Bend the larger of the 2 halves of each paper clip into a small loop. Hold one of your magnets on the inside of the cigar box. Place the other 3 on the outside. The strong magnetism will hold them in place. Leaving about 2 inches of straight wire, wrap 30 to 40 turns of the magnet wire around your cylinder. Carefully slide the coil off of the cylinder and cut the other end to about 2 inches. Wrap a few turns around each side of the coil to hold it in shape. Then reverse direction to form a loop and pass the wire through it. This will lock each wire in place. Straighten each end and make them as straight as possible. You can use the handles of the pliers to test the coil's balance. Using your scissors, carefully scrape away only the insulation on the top of each straight piece of wire. This will allow the coil to conduct electricity when one side is facing up, but not when the other side is facing up. This interruption in conductivity is necessary for the motor to operate. If the coil always conducted, it would lock into just one position over the magnet. Lay the coil in front of the magnets on your cigar box. This will serve as a guide for positioning the 2 paper clips. Position each paper clip as shown, making sure that the loops at the top align with the areas of straight wire that have the insulation scraped off. Secure each paper clip with the push pins. Clip each straight piece of wire to about a ½ inch and insert the entire assembly into the 2 loops at the top of the paper clips. Balance the coil as much as possible by bending the straight wire slightly if necessary. Attach one end of each jumper wire to the 2 connectors on your battery holder and attach the other ends to the 2 paper clips. That's it. Give the coil a gentle spin and your motor should start. If it fails to start, first try spinning it in the other direction. Next, you would check that the insulation is completely scraped off on the top half of each of the wires. And finally, check your batteries. If everything checks out, this is what should happen. Well, that's about it for this episode of Simple Science. I hope you had fun building this project, and I hope it gave you some ideas for some interesting conversations about magnetism and how it can be used. Thank you all for joining us, and don't forget to like and subscribe if you'd like to see more videos like this. See you next time.
That's a handsome man.
Oh, no doubt. Anyway,
has this guy gotten an oven mitt yet, Si?
No. Andy Jones is mitless. I can only imagine the kind of damage that he incurs when he watches some stupid flat earther. Anyway, now there you have it. That's this week's Simple Science. And back to you, Andy.
Oh, always a good time, Si. Your experiments are actually a heck of a lot of fun. I can't wait to break into the videos. I got some nieces that are a little bit closer than they used to be now, so actually a lot bit closer, like arm's distance. Got to push them away, but going to be able to start sharing some of these simple science projects with them, and I think they're going to have a blast with it. So.
I do hope so, and like I said, the end game is not the experiment themselves. Those are fun to do and all that. It's the conversations that follow, because eventually they'll look up and go, "I like what this thing's doing. Why is it doing that?" And then,
absolutely.
Then you get to have nice talks.
Very awesome. Well, I think that probably about does it. Tornado Pelt, don't worry, I'll send you a message after the show. Other than that, I think that might about wrap it up for the evening.
Okay, very good. Well,
Thanks for the invite, guys.
well, thanks
Yeah,
for
Hey,
joining
glad to
us.
have you on the show, Andy.
Thanks
For joining us again, Shawn. Always glad to have you guys with us.
I join when I can.
Yeah,
Well,
glad you both did. All
indeed.
right. On that note, closing time. Here we go.